Hello, everybody, and welcome to our Friday 13th edition of our NACE Calgary Zoom webinar series. I'm your host, Brett Johnson, Program Chair for NACE Calgary. So today's webinar features Arti Bhatia and Burke Delanty. Both of these people have been in the industry for over 25 years, working at various operating companies, and have been providing consulting services to operations for many years. We are very excited to have these two back as their previous presentation was canceled due to the pandemic. Thank you so much both for joining us today. So thanks again for joining us today. Can you tell us about your presentation today?
Thanks, Brett, and thank you, NACE Calgary, for inviting us back. We're sorry we couldn't have our in-person session on March the 13th, so Burke and I were hoping to hold off until an in-person session was available. Fortunately, that's not happening anytime soon, so we're glad to be here with this virtual session. We're going to be talking about engineering assessments. I'm going to handle the management system perspective of it, and then Burke will come on camera and speak to the technical assessments related to Clause 10 and ILI and defect and imperfection assessments specifically. So we look forward to presenting for you, and we also look forward to some of your questions, and feel free to ask us questions through the chat box or through Brett, and we'll certainly have some time at the end of our session to be able to answer them. So
just before we jump in that, one quick thing, I just want to give a quick thank you here to our annual sponsors. Their contributions would, they allow us to be able to do this whole webinar series and provide this at no charge. So today, I'd like to highlight our gold sponsor, ChampionX. So ChampionX is proud to be a gold sponsor of NACE and an active contributor to our NACE seminars, technical groups, and events. Their purpose is improving lives. So formerly Nalco, Champion Upstream, and Apergy, together their combined expertise is what differentiates them as an oil field equipment, chemical, and automation technology company. And of course, to all our other annual sponsors, they're a huge reason why we can do what we do. Our sponsors help fund several initiatives that NACE Calgary takes on to promote the knowledge of corrosion, sustainability, and asset integrity to the next generation of engineers. To each one of our sponsors, we thank you for your continued support. So to see this webinar and a few of our past webinars, be sure to check out our website at nacecalgary.ca. From there, you can get the YouTube channel link and all the details on all our upcoming webinars. So as Arti jumped in and mentioned, they're going to give their presentation live, and so be sure to stick around after the presentation as well. We'll move into a live Q&A channel. Please submit your questions to Arti and Burke using your Zoom client by clicking the Q&A button on the screen there. If you're joining us from YouTube Live, please enter your questions in the comment fields, and then I'll be sure to read them. And so without further ado, Arti, take it away. It's all yours.
Well, good afternoon, everyone. Thank you for joining us today. I'm Arti Bhatia with DNVGL, and Burke Delanty is also with me today, and he'll be on camera soon. We'd like to present two aspects of engineering assessments, and I will speak to the management systems components of engineering assessments, and then Burke will take over and talk about some technical guidance for EAs, as we call them. So why am I here talking about management systems when engineering assessments certainly are technical assessments? The reason is I'd like to say that a lot of the engineering assessments and the way it is reflected in the Canadian Standards Association Z662 is through Clause 3, which is the Safety and Loss Management Systems Clause. So no worry, we will not talk about management systems much in this, but I do want to speak to where it first comes up in the standard, and it is in Clause 3. And Clause 3 is a group of individuals involved in management systems that oversee Clause 3, Annex A and Annex B. And our representation is diverse. We do have technical experts, industry subject matter experts on management systems, and regulators from both the provincial and federal jurisdictions. So a nice little set of folks belong to the technical subcommittee that oversee Clause 3, Annex A and Annex B. And I do want to make a special note that Annex A, pardon me, we're downtown Calgary here. So I do want to make a special note that Annex A, although I've noted is informative, is actually mandatory through the British Columbia Oil and Gas Commission. So I'll get into a little bit more of the regulatory oversight on engineering assessments in the next few slides. So speaking about where engineering assessments first comes up in the standard, it is actually in clause 3.4. And as you can see, a pretty decent definition of engineering assessments exists within the standard. It's the first paragraph of the slide, and that's located in clause 2. So rather than reading it, I think I just want to ensure that everybody knows where it is and point to it. But it's certainly grounded in engineering principles and also the competency of the individual doing the engineering assessment. So the definition is quite clear. And then as a result of that definition, it sends you to clause 3.4. And clause 3.4 is there to help you develop your engineering assessment process in the context of a safety and loss management system. And as everyone's aware, there's many references to engineering assessments within the Canadian Standards Association. And there are some examples in the notes in clause 4, clause 5, and clause 10. But if you were to just search for the word engineering assessment, it would come up 165 times approximately, if not more. And so there is lots of avenues where engineering assessments are deemed appropriate. So I've picked out a few situations here where engineering assessments may be used. And so this bullet list is not exhaustive. It is a list of typically where we see most often engineering assessments occurring. For today's presentation, Burke is going to focus on bullet point 3, the suitability or fitness for service of an imperfection and defect. And we wanted to kind of give some good guidance there rather than trying to give general guidance on all of these. But I'll speak to a few of the things with respect to engineering assessments, and some of them in terms of their complexity and oversight and rigor that's required. But generally, this is sort of what we see more often than none where engineering assessments are used in the pipeline systems. So before I jump into a little bit more of the management system aspects of engineering assessments, I wanted to point out where the regulators have cited engineering assessment requirements. And this is not, again, an exhaustive list. What this is a few examples of where it does exist in the regulations. So for instance, with the CER, or the Canada Energy Regulator, they do have a very detailed filing guide E with respect to the change in class location per their onshore pipeline regulations, section 42. And there are filing requirements for an engineering assessment that are quite detailed. And if you note in various safety advisories that the CER has, they do point to the need for an engineering assessment. An example from BCOGC, or the British Columbia Oil and Gas Commission, is in their Oil and Gas Activity Application Manual, Appendix A, where they point directly to the requirements of CSA Z662, and they do note that assessments must be sealed by a professional engineer licensed in the province of British Columbia. And the last example, but not the only example from a provincial regulator standpoint, is the AER, the Alberta Energy Regulator, in Directive 56. And they do note engineering assessments required for pipeline resumption on discontinued pipelines. They also do have requirements for engineering assessments during transfer of assets and whether you have information and data when sale of an asset occurs or a transfer of an asset occurs. So the EA process, it is required to have a documented EA process as per clause 3, but it's important to make sure that it's practical to use in your organization and to understand, and definitely be scalable to a wide range of situations. The list I provided earlier is just one page of what could be many pages of scenarios where an engineering assessment could be used. So when developing a process, I think it's important that the process helps you be consistent with how you derive conclusions and recommendations, and also to adapt to the degree of complexity of the engineering assessment and the degree of rigor required in order to undertake one. Another topic that's touched on within CSA Z662 is the responsibilities of individuals performing and reviewing and approving engineering assessments and their qualifications. And that is definitely aligned with the classification of what an engineering assessment might be, whether it's a very simple one or more complex. And I'll get to some more information and guidance on how that is sort of offered within the standard. So very simple diagram. I've not decided to extract all the wording from the standard, but to just put it in maybe simple terms or my terms maybe. And there's probably 3 or 4 levels of engineering assessments that one might encounter. And some of them are very simple. Some get to be more detailed and require a little bit more thinking. And then there's ones that are quite complex or multifaceted. And the level of classification when you develop your EA process will help you kind of determine who needs to be doing the work, what their qualifications and training should be, and also who needs to approve and see that and be part of any actions coming out of an engineering assessment. So if you were to go to the commentary within CSA Z662 that's aligned with the engineering assessment clause, you'd be able to get a lot more detail about what the classification mechanisms could be and how you could go about using what's suggested in the commentary to develop it within your own company process. So examples of classification, because those were words that I just presented to you in the slide before, but this is actually maybe something that is a real life example of what we might encounter. A simple engineering assessment would be in, as a good example, a remaining life calculation where you have a lot of good principles, a lot of well-grounded principles and documentation. A more detailed type of engineering assessment may involve something with interaction of defects or hazards, strain analysis of dents, or even within the structural integrity of pressure vessels, tanks, or piping. A more multifaceted type of engineering assessment may be when you're encountering a class location change or you're entertaining the idea of increasing your maximum operating pressure or the operating pressure you're currently at to your maximum operating pressure. And those tend to be very complex and have multi-layers, multi-tiers to what type of analysis you may be doing. The other thing to consider when you're classifying your engineering assessment for your engineering assessment process is whether what you're trying to do is fairly new or whether it's been established and grounded in a lot of principles and documentation that the industry is aware of, where there might be some constraints or limitations to your situation. And again, like I said, if there's good guidance documentation that's established industry practice. Also, you may want to consider what will be the level of assumptions and inputs you're using for your analysis and any unusual or unexpected circumstances that might occur. More importantly, it's very crucial to look at the expertise of the individuals involved in conducting the analysis and their relevant background and experience. In a lot of cases, what you're doing may require a highly specialized person and or analysis, and that information may not be available, and a lot of the work you're doing may be considered one-off or very specific to your conditions. And if you have assumptions and inputs that are highly specific to your situation, you're often looking at a higher level or more complex type of engineering assessment that requires more scrutiny and rigor. So generally in industry, we have some great documentation for metal loss assessments and cracks that have good acceptance criteria associated with it. When you start to get into more complicated EAs and one that may involve risk assessments and both the likelihood and consequence analysis with respect to risk assessments, you may be wanting to ensure that you're demonstrating equivalent or better safety and reliability than what exists in the code. And the reason I put the second bullet in there is that's something that I think is sort of important within a class location assessment that you're doing. And as I referred you to Filing Guide E by the CER, they certainly have expectations on demonstrating better safety and reliability with class location assessments. So with respect to preparation, review, and approval of an engineering assessment, again, I tried to simplify what the expectations may be. Certainly something simple like remaining life, or burst pressure calculation may be something that can be done through your internal operating company expertise or through a consultant. Consultants are good too. But if you get into more detailed or more complex engineering assessments, you may not have that subject matter expertise in-house, or depending on the size of your organization, you may reach out to consultants or individuals that have a lot of expertise in that area. Definitely within the commentary of Z662, there are some suggestions of the type of individuals that would be preparing, reviewing, and approving engineering assessments with respect to registered technologists or technicians and persons with professional engineering designations. As you get to highly detailed, multifaceted engineering assessments, such as a class location change, certainly it is suggested to have appropriate preparer, approval, and reviewer be within the right subject matter expertise, but also within your organization have that level of seniority to be able to approve it and have the oversight of what's being considered within that engineering assessment, especially when it comes to the recommendations. So again, I think just some key things to consider when undertaking the review or an EA is to make sure that the appropriate responsibility and resources are assigned. Class location change or an increase in operating pressure certainly take a variety of types of people that may be involved in it, and they need to be qualified. And certainly I think it's important that the information that's put forth in an EA is properly documented and tracked. I think as well, the guidance in Clause 3, Annex A, and the commentary speak to the rationale for applying specific criteria and having that fully laid out in your engineering assessment, whether it be the criteria you use for assessing anomalies or remediating them, the establishment of inspection frequencies, or putting forth preventive and mitigative measures. Also very important and highly suggested and put forth in Clause 3, Annex A, and the commentary is a process for review and updating of your EAs. So certainly when you develop and put forth an EA, you've made certain input assumptions, and it's important to identify when those have to be reviewed, whether there's changes in inputs regarding your pipeline attributes, operating conditions, technology that's been involved, or within the codes and standards or regulatory requirements. It's important to brush off that EA, look at your input assumptions and what was put into putting forth those EAs and coming up with the conclusions and recommendations to make sure they're still valid. So this slide is moreover to help you with an outline of a complicated or multifaceted EA. And I think it's important to look at some of the suggested record retention and record sort of outlines that are suggested within CSA to develop a good framework for what should go into an engineering assessment. So I've highlighted a lot of this already in the previous slides, but I encourage you to look at the Z662 standard and some of the information it offers when developing your own internal process. So an example of a multifaceted EA would be, as I mentioned, something like a class location change or a change in operating pressure. And I think it's important from us to note, or myself to note, that a multifaceted EA certainly implies that you may want to go back and look at some of your design, manufacturing, and construction principles that were used within the pipeline or the asset. And I would suggest that it also says that you have to review a lot of what are your existing hazards and threats and what could be your potential hazards and threats. And definitely quantifying those and calculating consequences. For more complex EAs, I am highly suggesting that a quantitative risk assessment is important because it is important to look at both the likelihood and consequences of an undesirable event. I'm also suggesting that some of these risk assessments would involve failure frequency data from spills, doing outflow analysis, and looking at leak response from your valve spacing. As I close out the management system aspect of engineering assessments, I want to also connect the dots with where an engineering assessment and alignment of the EA process with your management of change process is very important. I think your management of change process is unique to your company or your organization, and certainly changes implemented based on how significant they are, how complex they are, should be definitely aligned with the changes required within your own internal MOC processes. And I think we're certainly not recommending that routine changes that are covered by standard procedures, such as pipeline repairs, are necessarily what we're suggesting are part of your MOC. But certainly when you start to look at class location changes and changes in operating pressure, you certainly have to look at how that is implemented through your corporate MOC process. So thank you very much for your attention. I really appreciate you listening to the management systems aspects of engineering assessments. And I'm going to turn over the next part of our slide show and presentation to Burke Delanty.
Good afternoon, everyone. Hopefully you and your family or families are getting through COVID as well as possible. As already indicated, there's obviously a number of different elements going into an engineering assessment. I thought that my talk would focus on how to assess metal loss, deformation, and cracks, either from an inline inspection perspective or from anomalies that are found in the field. So hopefully that, and it's our perspective on how to do these assessments. It doesn't mean it's the only way to do them by any stretch of the imagination, but it's just to give you our thoughts on how we would go about doing them. So the areas that I'll focus on is the assessment of the current acceptability of metal loss, cracks, and deformation, and the long-term acceptability of such anomalies. So there's a number of different assessment methods for determining the current acceptability of the three types of defects. So for metal loss, everyone knows there's ASME B31G, both the original and modified. R-string is probably the most predominantly used. And then there's some commercially available methods as well. It's just a matter of, as an operator, just being comfortable in which method you want to use. I think there's enough information out there indicating the performance of each of them, so you can make an informed decision on that. For cracks, again, there's a number of different approaches. The log secant, modified log secant, is kind of the original one, and a lot of them have been built off that API 579, deals with FAD diagrams, and then there's a couple of other ones that have been developed by other individuals, consulting firms. And again, there's information out there on the advantages and limitations of the different approaches. So again, one is free to choose which one they want to use. Regarding deformations, there's a recommended practice by API that just was recently finalized, 1183. It outlines the methodology to assess dent strain, which is from ASME B31.8. With regards to the assessment of current acceptability of metal loss, what we would call here, we call it a compliance criteria. So it's based on when you get the inline inspection data, or you find a defect in the field. CSA clause 10.10.2 provides guidance on, from both a failure pressure perspective and depth perspective, what the acceptance criteria is. It's easy enough to follow. Some of the key assumptions that we thought we would highlight for you, as far as flaw dimensions, Obviously, the actual field measured dimensions in as fine of resolution as possible is advantageous. Similarly, with inline inspection data, the flaw profile, again, with metal loss, both in the field and with the inline inspection vendor, the most that can be done to get the actual profile, so the river bottom profile, is it allows you to make the most informed decisions. So if you don't, you end up using 85% of the area created by the maximum depth and length. And that can be overly conservative. It's not that big a deal when making decisions in the field for repair, because it doesn't hurt to be a little conservative in making your repair decisions in the field. But when it comes to analyzing inline inspection data, I realize that it costs more for the vendors to provide the operators with predictive failure pressures based on the effective area approach. But ultimately, it might save you some digs, so you can balance the cost out of the additional analysis versus the potential cost savings from reducing the number of excavations that you have to do. CSA talks about corroded areas that contain cracks or are concentrated along an ERW weld seam or a flash butt welded long seam, or pipe that's expected to exhibit brittle fracture initiation. Our approach for dealing with it here is we treat the metal loss as a crack and assess as a crack, as opposed to try and assess it as corrosion. The assessment pressure for corrosion defects in an excavation, regardless of what you're currently operating at, it's best to assess those against the MOP of the line in case if you are operating below MOP and you choose to go back to MOP in the future, you don't want to have to go back to sites that you repaired to a lower pressure and have to address them. With regards to inline inspection data, the different options depending upon the amount and severity of the anomalies that are reported. Obviously, the first option is against the maximum operating pressure. If there's a lot of anomalies and they're severe that could require excavation, one way of prioritizing them would be assessing them against their site-specific maximum observed operating pressure or site-specific transient pressure. And the rationale behind that, if you can follow my, sorry about that. The cursor is these flat lines represent the MOP along the various segments of this example pipeline. And this line here is the pressure decay that you see along the length of a line. Now, it would be more pressure decay for a liquid line than it would be for a natural gas line. But if you do your assessment and your focus is on everything as a factor of MOP, at these areas down closer to the suction side of either a compressor station or a pump station, they're actually getting a larger relative safety factor, if you will, than anomalies that are operating closer to their MOP. So this would be a way of helping you prioritize excavations if the number of excavations becomes something that either financially you can't do or schedule-wise you just can't get done in the required time frame. As far as the current acceptability of cracks, as you know, there's no defined acceptance criteria presently in CSA set 662. We would recommend that the predicted failure pressure based criteria that's in CSA clause 10.10.251 for metal loss, we would suggest that that be used for cracks. You certainly wouldn't want anything less stringent than what's used for corrosion, given that the crack tools aren't quite as accurate as the metal loss tools. So it would be hard for me anyways to justify using a less stringent criteria for cracks. And similarly for crack, a depth-based criteria, I think again, for the same reasons I just mentioned for failure pressure, you'd want it to be more stringent than for metal loss. So as an example, you might want to set that as 60% of the wall thickness. Some of the key input assumptions for cracks, the flaw dimensions, the actual field measured dimensions. So this is one of the things that with our clients, we deal with a number of excavation programs that they do. The more that you can do to have your field NDE vendors provide you actual flaw profiles will allow you to be able to make more informed decisions about repairs, as opposed to them just giving you a maximum depth and maximum length, because it's unlikely that they're that maximum depth for the entire length, so you'd be making very conservative decisions. And that ties into, for the flaw profile, when you're dealing with crack anomalies reported by an inline inspection tool, we'd recommend that you use a rectangular profile for seam-related defects and a semi-elliptical profile for pipe body cracks. Some other key assumptions that come up, obviously, for cracks is the material toughness. It has a huge impact on the tolerable defect size. Ideally, if you had actual test data, whether that be from mill test certificates or lab testing of a given pipeline, if it's more recent pipe and you have your pipe specifications or the CSA pipe specifications that they were ordered to, that would be helpful. If you have information on similar lines, you could use that, or assumptions based on industry experience with vintage of pipe and type of seam weld. So there's obviously a number of papers out there where companies publish what input properties that they use for assessment. So it's just trying to find something that is as closely represents your specific pipeline given its vintage and the type of seam weld that it has. Assessment pressure for cracks detected in the dig, we'd recommend that the assessment pressure would be MOP. And for cracks reported by inline inspection, similarly to the metal loss, there'd be the three options. Obviously, MOP is number one, but you could use the other two as a way of prioritizing your digs if the amount of digs that you had was something that either was uneconomical to do in a given year or just scheduling wise you couldn't get done in a given year. And when we talk about cost, it's not that the decisions are based solely on cost. It's I think just about every operating company will make the money available to address anomalies that need to be addressed. So it's our job as the integrity engineers to help the senior management to make those decisions. So if you have very conservative criteria, very conservative assessment approaches, you make a lot of anomalies appear to require remediation that if you were to look a little closer might not. And so that's the idea of providing a means of prioritizing the excavations for you. So assessing the current acceptability of deformation anomalies, again, CSA clause 10.10.4 provides guidance on a long list of acceptance criteria for deformation anomalies. Again, with the flaw dimensions, the actual field measurements, measured dimensions or inline inspection reported dimensions would be advisable. I know that in CSA it talks about for inline inspection data that you're supposed to consider tool tolerances. I think when you're doing what we would call the compliance criteria, I think it's best to base it on as reported dimensions. And you consider tool tolerances once you've done some excavations, or as well you can consider them, well, you must consider them when you do the remaining life calculations. But I think developing a compliance program for inline inspection, incorporating the tool tolerances might be just a little conservative until you understand how well or how poorly the inline inspection tool size and accuracy is. Another one that needs to be factored in is, given that a number of the criteria under 10.10.4 for dense involves its interaction with metal loss anomalies and or cracks. So using the tolerances provided by the inline inspection vendor and the crack and metal loss inspection vendors regarding the length and width sizing accuracies of the respective tools and the axial and circumferential position accuracies of the respective tools. You use that to try and determine whether a dent is actually interacting with metal loss or actually interacting with a crack. Regarding the assessment of long-term acceptability, the bullets on this slide would apply to all defect types. So obviously in determining remaining life, there's a deterministic approach that one could use, and there's a probabilistic approach one could use. I would suggest that which one you use is dependent upon the amount and quality of required input data. So if you have very limited data and it's not of the highest accuracy, I think you'd only be fooling yourself if you were to try and do a probabilistic remaining life assessment. Whereas if you have a lot of detailed information for the various input parameters, then you might benefit from doing a probabilistic assessment. Input assumptions for deterministic remaining life assessments. We'd recommend that you make as accurate or realistic assumptions as possible for each of the various input parameters. If you were to make conservative assumptions for each of the input, or overly conservative input or assumptions for the various input parameters, you're going to end up with a grossly conservative remaining life assessment. And again, the goal of these assessments is to help identify the features that really need addressing now versus the ones that can be addressed in subsequent years. The safety factors applied to calculated remaining lives. So our recommendation would be to calculate the remaining life to the date of failure, and then you have a couple of options. You can take the half-life of that remaining life, or you can take the predicted failure date and minus X number of years. So if you have 10 years remaining life, you could decide that you subtract 2 from it, you subtract 5, whatever the company feels comfortable with from a risk tolerance standpoint, and again, from the quality and the amount of data that you had that went into the remaining life calculation. Again, with regards to the long-term acceptability for all defects, the sizing accuracy, there's a lot of discussion about doing validation digs. They're obviously a good idea to understand the performance of the given tool and the given line. But if you're going to do a validation program, it needs to be, the number of anomalies being excavated for validation needs to be statistically determined. Obviously, doing an excavation, one excavation that involves a few anomalies isn't going to be able to allow you to convince anyone that you have a validated sample size for assessing the accuracy of the tool. So if you don't have enough field data, then you use the stated tool tolerances, and you can do sensitivity assessments in your remaining life calculations where you use 1 tool tolerance, 2 tool tolerances, 3 tool tolerances, and just understand the impact that has on your remaining life calculations. If you don't have any excavation data for the given pipeline, but you've run the same technology in one of your other lines recently, and you have validation data for that, you could use that as a basis for determining what the sizing accuracy might be of your given tool line. So this is just an example plot for you, a depth-based plot. This one happens to be for metal loss, but it could also be for cracks or dents. The solid red line is what you would get from a regression, whether it be a linear regression or a reduced major axis regression analysis. This red dotted line and this black dotted line is a prediction interval. For this example case, we have it as a 95% prediction interval, which means that 95% of the data that you see plotted here is going to fit between that dotted red line and the dotted black line. And in that sense, 2.5% of the data would be predicted to fail or predicted to reside above this dotted line. So if you're doing a deterministic assessment, we would strongly recommend that you use an approach that involves a prediction interval. Again, the percent confidence that you have in that will be somewhat client or company dependent. We would advise against using a linear regression when doing a deterministic assessment, because obviously, as you can see by these data points, half of them are going to be above the regression and half of them are going to be below. In other words, half of your calculations will be non-conservative. And the goal here obviously is to prevent failure, so we don't want that. But this linear regression could be used in probabilistic assessments because you'd use that linear regression along with some of the correlation coefficient and prediction errors, which gives you an idea of the spread of data, and you could use that in your probabilistic assessment. And then this is just a similar example for failure pressure. Again, this would be applicable for metal loss and crack anomalies, but obviously not for deformation anomalies. And in this case, if you're using the deterministic approach based on a prediction interval instead of the upper one, you would use a lower because we're looking to lower the failure pressures, not increase them. So those are just a couple of examples of how you could use field tool correlation data. Now, some specifics about the long-term acceptability of metal loss anomalies reported by an inline inspection tool. So there's a number of different approaches currently being used for determining corrosion growth rates. One is feature-to-feature matching from a successive inline inspection runs. Those are typically done by the inline inspection vendor themselves. You can do statistical analysis of the reported depths from successive runs. There's a number of companies that offer that service. There's simplified comparison of successive inspections. So that could be on a joint-by-joint basis of successive runs. You compare the maximum depths reported on the joint or the average depths on the joint. And obviously in each of these cases that you're using successive runs, you're taking the time difference between the two runs, and that's the denominator in the crack or the corrosion growth calculations. There's time average corrosion growth rates that you can do. So based on the reported anomaly depths from the inline inspection tool, you can take those depths and you can take into consideration the age of the pipeline and make some assumption as to the number of years for the corrosion to initiate. So you have to allow time for the external coating to respond and then for corrosion to initiate. Obviously, if it's internal corrosion you're looking at, the initiation point for that can be the day that the pipeline went in service. NACE also has some recommended values depending upon whether it's a protected pipeline or an unprotected pipeline. Regardless of all of those, it's our recommendation that you set a minimum corrosion growth rate threshold regardless of what's calculated. So it might sound great if the calculated growth rate is 0.001 millimeters per year, but it's best to set yourself some threshold as a check against any errors that could have happened from the growth rate determinations. And for us at our shop, we use 0.1 millimeters per year as a default corrosion growth rate. Now, when it comes to doing remaining life assessments for both cracks and deformation anomalies, it requires the assessment of your operating pressure data, so representative pressure data. And so this is just a brief description of the quality checks that when you do start to look at your pressure data, first of all, you want it in as fine an increment as possible. Daily pressure data is really not useful when it comes to doing pressure cycle counting. So you want it in as fine an increment as you can. The easiest thing to do is to create plots like this top one so that you see all the data. And then the idea would be that you would investigate internally these values that seem to be outliers relative to the bulk of the data, determine whether they're real data points or if there was issues with the pressure recorder. Out of that resolution, you end up with the pressure data that you're going to use for pressure cycling, which will be described in the next slide. So ASTM has ASTM E109 or 49-85 has an approach for what's referred to as cycle counting of the pressure data. So it takes all of these cycles that you see here and breaks them down into bins as far as the magnitude of the cycles. And you see the cycle counts that this is just an example again, but you set your range of cycles or the magnitude of the pressure cycles, and then you just, the ASTM standard, the approach allows you to calculate how many cycles are within each of those bins. One of the key things when determining remaining life for crack anomalies and deformation anomalies, when you're going to project what your future operation is, it's important to have a good handle on what that is. This is just an example from a pipeline that obviously has been going through some different operations over the years. So it's important to know, is the future operation going to be more like the last part, or is it going to be more like the first part? because that has a huge impact on the remaining life calculation. So having a firm understanding with your control center as far as, or your business group as to how you expect the system to operate moving forward is needed in order to be able to do these calculations. The recommended approach for determining crack growth rate, fatigue crack growth rate, is used in the Paris Law method. It's been well established, and it's outlaid in ASME B 579. With regards to environmental crack determination, so please refer to the SEPA SCC recommended practices for guidance. In there, they mentioned there's growth rates based on industry research. It's unlikely that many operators these days are doing their own research. There's growth rates can be calculated based on empirical correlations that take into consideration the crack dimensions and the severity of the pressure cycling. You could do time average environmental crack growth rates based on the reported depths of the anomalies, much like we talked about with metal loss and the age of the pipeline, and then making some assumption as to an initiation period. When it comes to combining fatigue and environmental crack growth, our recommended approach is to grow the anomalies in discrete intervals. And during that interval, whichever the cracking mechanisms results in the faster growth rate, you apply that during that time interval, and you keep doing that until the failure date is predicted. One of the things when Arti was talking about the different forms of EAs that might happen, there's cases where you might want to increase the pressure if it's been operating below MOP, but it's a line that isn't piggable from a crack tool perspective. So you have to have some means of assessing the threat of cracks in that pipeline. There's something called a just surviving flaw analysis, where you take into account the hypothetical worst case crack that could have survived a commissioning hydro test, or if a subsequent hydro test has been done for some reason. That helps you set the baseline of the size of flaw that could survive the hydro test. So this is an example of it. What you would do here, the curve on this curve here just indicates at the MOP the length and depth of a flaw that would fail at MOP. Our recommendation is, if you were to have to do this kind of assessment, you determine the length for this based on the leak versus rupture length at the MOP. Turns out, based on our experience, that that length has the shortest remaining life associated with it. And then when growing cracks, we recommend that you assume a constant length, or the length remains constant. Using a constant aspect ratio is overly conservative. If you start off with a 100 millimeter long crack that's 1 millimeter deep, so that's a 100-to-1 ratio. If you now say that it grows 1 millimeter more in depth, so you're now 2 millimeters, all of a sudden you've made that crack that was 100 millimeters long 200 millimeters, and that's just not likely to happen in the way cracks grow. So that's why we recommend that you keep the length constant when you do these remaining life calculations. And so then all that happens is you now determine what depth at that leak versus rupture length would just survive either the commissioning hydro test or a subsequent hydro test. And then that's the depth that you start with, and then you grow it from that depth to when it would fail at the MOP. Okay, with regards to determining the long-term acceptability of deformation anomalies, the recently finalized API Recommended Practice 1183 provides guidance on this. It incorporates research that was done by INGA, the PRCI MD4-9 method, and guidance that's provided in API 579. Regarding determination of reinspection frequencies, this is another issue that comes up frequently. There's essentially two approaches. One is a predefined frequency for all inspections. Typically that seems to be 5 years. This has the potential to either be too conservative or not conservative enough, or require a large number of excavations to ensure the continued integrity of the pipeline during the predefined interval. The other one is reinspection frequencies determined based on the remaining lives of the reported anomalies. This would allow you to do a cost-benefit analysis to determine the most appropriate reinspection frequency, taking into account the cost of the excavations, the reinspection, and the number of excavations required to achieve a given reinspection frequency. So again, it's not a matter of saving money for the sake of saving money, but it's of the money that you have is trying to make the best informed decisions that you can and make sure you're spending the money assigned as wisely as possible. So our preference is to base it on the remaining life of the anomalies. And we think that that will allow you to better use the funds that you're allotted. So that's my presentation. Hopefully I didn't go through it too quickly. Brett, we'll open it up for questions now.
Great presentation. Thank you guys both so much for that. We are running a little bit out of time, so we'll probably need to jump through this. We might run a little bit late here, but jumping to some, so everybody please submit your questions through the QA channel or Zoom, or comment on YouTube Live, and we'll try and get them in the time. First question is for you, Arti. So in your opinion, what is one of the key things you want to consider before you embark on an EA?
Thanks, Brett. Sure. The question is an interesting one. There's a lot of things to consider before you embark on an EA. I would suggest, just from personal experience, know what you have in terms of data and information. That's actually going to dictate where you go, what path you take. Certainly Burke's demonstrated lots of assumptions, lots of ways you can go, but that's all grounded on what type of information you have on your pipeline, whether it's MTR based, whether you're making assumptions. And so, yeah, I think simply answered, it would be doing a data gathering effort.
From a management system point of view, so how does one prepare EAs for fitness for service when you're doing annual programs? So like, for example, if you're trying to create dig programs for either corrosion features or other things, you know, you've got, you know, you're going to have criteria based off your ILI data, your operation selection. You know, how would you provide some guidelines on how one might document their EA to prove that they're doing this on an annual assessment basis?
Well, sure. I think it's important to look at the framework that I suggested. There's a lot of information there that is generally available, but it's also how you compile your information. So the framework I suggested talked about your scope, your purpose, objectives, input assumptions, references, and I get it. It's a lot of work to put information into an EA. But EAs are supposed to be living documents as well. They're not necessarily supposed to be a stop. And so if you're doing this on an annual basis, I think it's important to look at, to be honest, templating things, to look at where your information's coming from, when new information arises, such as field tool correlations coming from digs, new inline inspection data, whether you are assessing your pressures on an annual basis and whether your cycling has changed. It'll be important to start with your framework. And yes, it is a lot of work to document, but I think it's worthwhile effort to see where you have to go and where you've been.
No, fair enough. No, thank you very much for that. So this one here is probably for Burke there. So does CSA allow for at-site pressure when you're trying to assess your corrosion features? Often through CSA and a couple of clauses, they usually try and relate to MOP of the pipeline, but you had one slide on there where you kind of showed how the at-site pressure would change as you go down, you know, as you move further away from your pump from your pump station, and do regulators accept that? I know it can help
You're right.
prioritize.
Yeah, you're right, Brett. It's not mentioned in CSA, and some of the regulators here in Canada do, some don't. And even if it's not used for the final acceptance, again, if you end up with a lot of anomalies that could require excavation, using the analysis at site would certainly help you prioritize them, because if there's a large number that you can't get done in one calendar year, or you can't get done within the budget, then at least that gives you a way of prioritizing which ones really need to get done from a structural integrity standpoint.
Awesome. So in the nutshell, you couldn't prove to a regulator to say, oh yeah, no, it's above that site and therefore we're fine.
Well, I think even for some of the regulators that don't accept it currently, I think if a company was to do a transient analysis and demonstrate what is the worst transient profile you could get on your line and use that profile, then you have a justification for saying, even under all these different scenarios that we ran in transients, we can't exceed this line. Then hopefully the regulators would be on side with that.
Awesome. Well, thanks for that. So another question for you, Burke. So this one's related to bending strain. Bending strain has kind of always been recognized as a potential threat to the pipeline, especially dealing with any kind of geotechnical hazards. Do you have any insight of whether or not there's any kind of what they might call an acceptable magnitude of bending strain, and then how one might be able to manage if they run a bending strain assessment on their ILI? What do they do with that?
So bending strain on its own, you mean, Brett? Not bending strain associated with dents, I'm assuming?
Well, maybe talk about both. The question specifically does not mention dents, but perhaps maybe that's your answer, is that it doesn't matter unless there is a dent. Yeah, so for dents, I don't have it right in front of me, but the clause in CSA that deals with assessing dents with bending strain gives you sort of the acceptable strain value for dents. It helps you determine their acceptability. Using bending strain for a geotechnical program, I think, yes, there is a standard. I want to say it's ASME. Sorry, I have it written down somewhere for some of the work we do, but there is guidance on what an acceptable strain value would be. I think you wouldn't want to do it based on just a single run. You'd almost need a baseline or successive runs to understand if you're having a change in the strain value, as opposed to just one value, because you don't know if that strain, the calculated strain, is from original construction or if it's from slope movements. So it'd be, as a minimum, be worthwhile overlaying the measured strain values with a company's geotechnical program where they think they have geotechnical hazards. Okay. I think that's good. I think that mostly answers it. No doubt it's kind of one of those things that it's data people are collecting and they're not sure what they should be doing now that they have areas identified with that. Obviously that can, potentially be to other things like circumferential cracking or something like that too, depending on the age and loading of your pipe.
Yeah, and that's where I guess if you have your first run of IMU data and you end up with strain data and you see relatively high numbers, the first thing would be to check to see if those align with areas that you think are active geohazards. If they're in areas that aren't active geohazards, then you need to probably go back to your ILI vendor to understand sort of their baseline strain values. Again, once you have confidence, so it probably takes successive runs to have an idea of areas where there's active strain. Once you have an idea of where there is active strain, then obviously, as you say, you can use that to help develop a circumferential SEC direct assessment program if you wanted, or to identify potential lines that could be susceptible to circumferential SEC depending on their external coating. I think it's hard to do much with one IMU run. You actually need to see the delta.
And that's a very good point on that. So no, I think that's good to help bring up, to help provide some clarity on that. All right, so I think most of these are for you there, Burke, but another question here for you. Sorry?
No, go ahead.
Okay. So in your experience, do you find that regulators often prefer to do what might be considered front load safety margin, like adding in ILI tool tolerance, for instance, within the EA, or would they prefer to see, what we call back loading safety margin? So this would be, after you've done the assessment and you know how many years you have to failure, say, okay, we're going to subtract, we're going to manage this X number of years before the predicted failure.
In our experience, I mean, the regulators can obviously speak for themselves, but our experience with the regulators is they, much like Arti laid out in her presentation, they just want to know that you have a process that isn't a shot in time. So they want to know that you're evaluating your data and that you're making the best decisions possible. So I think adding all kinds of conservatism for every input assumption is obviously the simplest thing to do, and it may appear to be the easiest thing to do, but it's actually not the most effective thing to do, because if you make every one of the anomalies be a question, you're really not making any differentiation between which ones you really need to do and which ones aren't a concern for X number of years. So in the work we've done with our clients here in Canada and through all the different provinces and with the CER, my belief is the regulators just want to see that you have a well thought out process, and if each step is defendable, they seem to be quite comfortable with that. I think where companies can get themselves into trouble is if they do an inspection run, they don't do any validation, they don't do any remaining life calculations, then I can see that the regulators would have issues with them. But if you have a program that assesses the defects as reported, then takes into consideration tool performance, and then does remaining life calculations, and has a basis for assigning a safety factor on that remaining life, they seem to have been agreeable, at least with the clients that we've been working with that have been dealing with the regulator.
Good point.
Long-winded?
No, I think that's great. I have one last little questions here, and then I'm probably going to shut down the QA line here as we're a little bit over time. But these should be both pretty quick. So on one slide, you mentioned that the minimum recommended corrosion growth rate is 0.1 millimeters per year within match features. So just for some clarification, if you've got two ILIs and you've got call it vendor matched feature to feature ones that report a corrosion growth rate much less than 0.1, should you still be using 0.1?
The reason that we have a minimum value is in my former life, there was an operator that did this pit-to-pit matching, and they ended up determining a growth rate of some ridiculously small amount of 0.008 millimeters per year. And that's what they used in the remaining life calculation for that anomaly. And it subsequently failed in service. So at the time, it probably made sense because that's what the math said. But after you have a failure, it's kind of hard to defend using a corrosion growth rate that's basically zero. The other thing to caution with pit-to-pit matching is in some of the pit-to-pit matching, we've seen negative corrosion growth rates have been calculated. So if a negative growth rate is calculated you have to have some question as to the positive growth rates that are calculated as well. So I urge caution when using pit-to-pit. And generally, at least in our experience, the pit-to-pit matching is only done for a certain number of anomalies. It's not done for the entire inspection run. So I would say proceed with caution if using pit-to-pit, and it's not anything against inline inspection vendors. But when you have a negative number that results, you have a hard time convincing me that the positive numbers are correct.
What if you're using a probabilistic assessment and would account for that unknown by assigning a standard deviation to your corrosion rate distribution?
Again, it comes down to, like we said, about the quality of the data that you have. If you have enough data and you can validate that these, because in essence, if you have a really corrosion growth rate, you're essentially saying it's not corroding. So if you're comfortable that either based on your CP data or something that you don't think you're having corrosion growth, then go for it. Using 0.1 millimeter isn't going to take something that's 10% and make it a problem right away. So I don't see it really hurting, but that's our example. I mean, setting a minimum value, I think, is appropriate, whether it's 0.1 or something else that's justifiable, I think is the right way to go.
Fair enough. And so that kind of leads into the last question we're going to answer is, have you ever used ILI signal analysis to justify crack growth rates?
What kind of growth rates?
Cracking growth rates.
No. So like I mentioned about why the acceptance criteria for cracks should be more stringent than for metal loss, the sizing accuracy of the crack tools isn't at the same place that it is for the metal loss anomalies. And so there really wouldn't be a justifiable basis for comparing depths reported from one crack tool run to another.
Okay. No, perfect. No, thanks. I really appreciate all the great questions that we got today. Thank you both for such a fantastic presentation and all the great answers to all the questions that came in. So we're going to close things down, but just to let everybody know here, we have a couple more upcoming webinars scheduled. On Friday, November 27th there, we have Sankara going to be presenting. And then on December 11th, we're going to have Dr. Frank Chang present. So please be sure to keep watching our LinkedIn and watching for our emails as we post up the registration sites closely for that and the details on what kind of presentations will be there. If you yourself are interested in joining us here with our presentations, please email me at program@macecalgary.ca, and I'd be happy to chat with you and see if we can get you on. So thanks again, everybody, for joining today. Again, great set of questions and great presentation. Watch us on YouTube for when we'll post this later, and have a great day. Thanks, everybody, and stay safe.